Okay. All right. So we'll kind of finish this up a little bit. Good thing about technology, makes things convenient and kind of nice and efficient for us. The bad thing is when it crashed. So that's exactly what just happened, and everything I recorded is no longer there. Sorry about that. Doesn't happen all the time, but this sometimes it does. So anyway, we were talking about domains. So let's do this. Let's look at finding domains from a graph. All right. And to do that, we're going to go back into Desmos again. So what I have found is that this poses issues for most people. It's kind of hard to find domains from a graph. And I don't really have a great way of explaining it. I wish I did. I've tried a couple different things, and so anyhow, I wish I had a magic, but I don't. So I'm going to go y equals, and I'm just going to go start off with a line because it's the simplest one. All right, so here's a line. All right, so domain, let me move this over here a little bit. So domain is x's, right? That's our inputs, okay? So if I was to draw a vertical line straight down in every single x, all the way. So basically we have this solid screen here. Every number on the x-axis would be covered, all right? And sometimes I tell folks, well, if you take your graph and you move it this way, it's going to cover everything on the x-axis. So we would say that the domain is all real numbers, all right? And even though it doesn't mention range too much, same thing would happen on the range, okay? If I went this way, this way, this way, it would cover everything. So we would just simply say that the domain and range are all real numbers, because those are all the numbers on the axis. All right? So this domain and range, all real numbers. If we go with what we call a power function, so here we have this thing, a parabola. Again, if I bring this all the way down here, no matter how much I zoom in or zoom out, okay, this is going, it's going to keep going. If I bend it down, it's going to cover everything on that x-axis. So we would just say the domain is all real numbers. Right? The range, however, stops here. So if I fold it inside, the range never comes down here on the y-axis. So I would just say that the domain is all real, yes, but the range is only positives. Okay, it's only positives. So if I move this to a 3, here again, this is going, it's just so steep that eventually it's going to get out to 10, it's going to get out to 15. If I go this way with it or compress it down, okay, it's going to cover everything on the x-axis. Definitely going to cover everything on the y-axis. So we would say all real for those. So what about something, let's look at something that oops. Okay, this one's a classic one. All right, it starts here and it keeps going, right? So the domain, down, 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 fold it down. It's going to be all positive real numbers, right? Because it never goes down over in this area. Okay. So graphically, you can kind of look at functions to figure out what the domain and range is. And what you'll hear from me a number of times is, You have to find your way to get these problems right, okay? I'm not really concerned about how you do it, as long as you understand it and that you can do it and get the right answer, okay? I'm not really big into doing a lot of drill and memorization. In fact, I don't like memorization. I like understanding. So what I try to do is teach you the concept behind what's going on, all right? So if you find it easier to do these problems by graphing them, by all means, graph them. If you find it easier to look at them and figure it out more of an algebraic way, which I'll show you here in a couple minutes, then do it that way. It really doesn't matter to me which way you do it. What matters to me is that you understand it and you can get it correct. All right, so let's do one more. I'm going to turn this off, come down to here. All right, y equals, and I'm going to put one of these in, which is the last thing that we talk about in this whole class. But they bring them up in this case. So this is a wild looking guy here. We got this, okay? This is a rational function, all right? And if I follow along here, I see that I'm getting close to 1 if I look at the x, but I'm not hitting 1, okay? Same thing happens up here, all right? I'm getting close to 1 on the x, but I'm never ever going to touch 1, okay? So we say the domain of this is all real numbers except 1, and you can't have that, all right? So it's hard to see it graphically on this because you kind of got to, let's see, it looks bending, it's bending. What is it? I can use Desmos and I can kind of create a point for using it with your phone, your finger. Okay, you can maybe get it, you could see, well, it's getting close to this 1 value, but it's not ever really touching it from what it looks like, all right? So some graphs are kind of easy to tell, some maybe not so much. If we switch this a little bit and look at this from a graphics or from a algebra point of view, y equals, I think that first one is something like this. Doesn't really matter. I'm going to go, let's go. What's this one? Plus 1. So it looks something like that, okay? That's a line, and so, you know, you can look at it and say, well, geez, there's really nothing I can put in here for x that's going to cause me a problem. All right? I can put 0, I can put negatives, I can put positives, I can put fractions, I can put anything I want. I'm still always going to get an answer. Okay, so we would just say domain, all real. Okay, or you can just go double bar R, which stands for all real. All right, so when you're doing your problems, test, quiz, whatever, that's all you got to do. Just do that. All right. Let me do this. Let's try one. Let's say we have y equals the square root of x plus 2. All right. And we want to do the same thing. So we want to figure out what the domain is. Okay? All right. But I don't want to graph it for some reason. I just have this thing about I don't understand graphing. So, okay, here we go. X plus 2. So, what can't we take the square root of? What kind of numbers? I can't do negative. Right? So what negative number would I put in here for x? That's going to cause me a problem. Negative 2. Good question. With negative 2. So negative 2 plus 2 gives me 0. Is 0 okay? 0 is okay. Negative 2.1 though, it's going to cause me a problem, right? So I would just say, well, I can't have negatives underneath here. So if I'm the type of person and I got to have a formula, you know, math is full of formulas and I got to have that, man, you give me a formula, I figured out. X plus 2 has got to be greater than or equal to 0. Okay? Or not greater than or equal to 0, just greater than 0. X, I'm going to subtract 2 here. Subtract 2. X has got to be greater than negative 2. Okay? If you're that type of person, that's how you're going to understand these, go for it. All right? If you want to visually see it, graph it. It doesn't matter to me how you do it, okay? But we can't have a negative 3 in there. We can have a negative 2, but as soon as we go negative 2, why is this greater? God dang it. Less than 0, my bad. Okay, less than 0, we're having an issue, all right? Y equals 3 over x plus 1. So I'm making up another one here, all right? Okay, I'm interested in the domain. So I look at this one. All right, here's a rational that they throw at you, okay? When are we going to have a problem with this fraction? When the denominator is 0, right? So when this is 0, I got an issue. So all right, I'm going to take this bottom part. I'm going to set it equal to 0. And, oh, man, when x is negative 1, I get an issue. So I'm going to come up here and I'm going to say x cannot be negative 1. All right. Now, we could have graphed it. Probably would have figured it out. But maybe you don't want to do it that way. Okay? Or maybe you want to do it both ways. You just love doing math problems. All right? So, you want to do it both ways. All right? But when you're going to run into some problems in the assignment where it's going to say, hey, find the domain of these functions, and you just got to find a way. All right? Let's make one a little more complicated. I see here they have one like this. So now they have both a square root and a rational. Oh my goodness. So let's deal with the rational first. What can't we have down here? Can't have a 0 down there, right? So x cannot be what number? Negative 1. Okay? So, okay, I took care of that part. What can a square root be? Negative. So now I'm going to say, but, doggone it, this has to be a positive number. Okay? Has to be a positive number. So, we could do a couple different things here. We could do some, oops, come on, go away. If we multiply by an x plus 1, we're going to lose our x. So we basically want to figure out when this is going to be a negative, all right? Negative 1 we already can't have. Anything positive is okay, all right? Could we have a negative 2? Would that be okay? What if we had negative 2? Would that work? No, we're going to get a negative down here, right? How about negative 1.5? Would that work? No. So we got to make sure this x plus 1, all right, is not negative. The 2 is always positive, so we're okay with that. So if we say, well, now I got to make sure this is always positive, so x better be just greater than negative 1. We already said it can't be equal to it, all right? Now we're going to say, not only can it be equal to it, but it's got to be greater than negative 1. And we're okay with that because we're not saying that it's equal to it. We're saying it's got to be greater than it. So this would be our final. All right, so in this case, all right, you got to look at both cases where you can't have a 0 on the bottom, and it's got to be a positive number, all right? All right? And you could have graphed it, okay? Could have graphed it in Desmos, and you would have seen, guess what? You would have got this, okay? I would have guaranteed it. You would have saw it, all right? So it's your choice. I don't care how you do them. I'm not going to tell you how to test the quiz. You got to do it this way. It's just going to say find the domain. What do I care how you do it, as long as you get it. All right. Do you want another one like that, or are we good? You want another one? Okay. Okay, 1 over x plus 2. All right. Well, first of all, what can't we have in the bottom of that fraction? Well, we can't have, but just look at the bottom of the fraction. Forget the square root. What can't we have in the bottom of that fraction? Can't have 0. Okay? So x cannot be what number right now? -2. Can't do it, okay? Can't do it, because as soon as I put a -2 in here, -2 plus 2 is going to give me 0. Can't have 0 down here, it doesn't work. All right? Okay. Now I go, well, but shoot, I got a square root, so I got to make sure that this is always going to be a positive number. Okay, so whatever I get here, it's got to be positive. All right? The 1's not going to change anything for me because it's always positive. So really, I just got to take a look at the bottom and make sure that I'm keeping that always positive. All right? There we go. So there's my domain. But you say, well, what about this? Well, but you're saying that. You're saying x has got to be greater than -2. You're not saying it's greater than or equal to. You're saying it's greater than -2. So it's not going to be -2. So we're okay. Right. Right. And if we switch here, I'll show you this. So if we jump back over this way, here, let me get rid of some of this stuff. It gets kind of cluttery. So, and you, by the way, if you want, you can do this. You can go f of x. This is kind of slick. F of x equals, and then you can put the function in there. Let's see, we had square root of 1 divided by x plus 2. Yeah. Okay, so here it is. All right. It's not ever. Come on. Oops, I lost my point. I don't know what's going on. I don't know. Anyway, I lost my point. It came over here and it went away. All right, maybe I can keep it up. It disappears. I think it's because it's shooting straight up, so it doesn't understand what I'm doing. All right, I'm going to change this to a different color because let's go with red. So here, okay, this is just never going to get. See, there's 2 right there, -2. It just slides right along. Never touches it though. Just slides right along it. Okay. Another thing you can do, if it helps you out, if you go to this plus here, you can add a table. Okay, and we could go up here. You can actually put this function in. I think if you go like this and go f of, I'm going to try this, f of x1. Okay, and then I come over here and I put some numbers in there. So -3, oops, -3. Why is it saying? Maybe I can't do that? I thought I could.
Well, the graph wouldn't let you go to 0.
Oh yeah, maybe because of this. No, I should be okay because this is f and this is x1. And if I put some -3. Oh, I know what's going on. It's not a numlock. -3, -2. It could be because this guy is down here, maybe? I don't know. It should work, but I don't know why it's not. Okay. What's that? Yeah, I added a table. So to this?
No.
To this?
On the side.
On the side?
Yeah, there.
Right there?
Yeah. Then you add it.
Oh, yeah.
Oh,
They added some new functions to this thing, and I didn't even seen that before, so that's awesome. That's awesome. That must have been something they just put in because I don't think that was there. They just added some things like about a month or so ago, so I really don't know if I've ever seen that before. But that's pretty sweet. Okay, so then that helps you too because, right, you got that undefined one right there, and it works for all the rest of them. And notice that it doesn't go anything, right? Everything is after this, okay? So shoot, that was great. Thanks for telling us that. So now you got like 3 ways to figure it out, right? You can do it by hand, you can do it by graph, you can use this cool table idea. Man, that's awesome. I didn't even see that. I'll show that to my coworkers. They're going to get excited about that. Okay. All right. So there's that. Any questions more on affine domains? Okay. I'm hurrying. I mean, I'm trying to get through things for you here. So there's a lot of stuff in this first section. We're not even done with it yet. All right. The other thing they have you do, and this is pretty straightforward. Is they have you do operations on these, okay? So they go like this. Now, here's how they do it. And this is what's messed up my class last term. This is how they write it in the text. All right? This is how I would write it. So, here's
they want you to foil it.
well, we're just going to add these guys. But here, the textbook does this. All right? So, that, you know, that's how I wrote my first quiz up. And I said, hey, we're just going to do this. And then everybody pretty much got it wrong. And I said, you mean if I wrote it like this, you guys would have got it right? And they said, yeah. And I said, okay, we'll just do it like that from here on out. Because to me, that makes a lot more sense. And this is kind of how it's usually written. I mean, it's not like I'm making something up. Most textbooks do it this way. All right, they go, hey, f of x plus g of x. But this is saying the same thing. Okay, so they're just saying the same thing. They're just doing it a little bit differently. So here, we're just going to take 3x plus 4 plus x squared plus 1. Okay? And then you just add, you know, collect the right terms and have at it. All right? But these two things are saying the same thing. So when you get to the book and you see that, all right? Oh, they're just telling me to add these two things. All right? I'm going to write it like this because the other class thought that was the way they understood that better. And I want to make it so you guys are successful. So I'm going to do it like that. Okay? If they put a minus in there, we're minusing them. Okay? If they do this, then we're doing this. And this is where we're going to FOIL. And you were right. So let's see, I got to get my x plus 4 times x squared plus 1. Okay? That's where we would FOIL. All right? So you'd want to FOIL it, you know, and get the answer. Ta-da, there it is. All right, so if they have it where it looks like this is what they mean. Okay? That's what they mean. Then we just FOIL or add or subtract or whatever they want you to do. Okay? And they're asking for the domain, but that's not any different than anything we've done before, so it's just pretty straight up. And that is finally the end of 1.1. All right. Woo. So I just drive, and then when I'm done with class, usually a friend of mine, and we get together, we just ride around here. But if it's obviously if it's like that, I'm going home. Okay, so the next thing that they talk about is the graphs of functions. So they do some things. The next couple of sections are actually pretty much on graphs of functions. All right. So the thing about this is they mention zeros and just getting information. Again, it's not a whole lot different than what we've been doing. Okay. So zeros are the same as x-intercepts. Pretty much. Okay. Zeros are also what makes the equation equal to 0. So it's like a solution. But anytime we have an x-intercept, right there, and right there, and right there, they call those zeros. Okay. Now, this text is really excited about y-intercepts. The only time a y-intercept really means anything is in a line, but they like it in all kinds of situations. All right. I'm not going to ask you for y-intercepts because there's no reason for me to do it if it doesn't have any real meaning. Maybe when we do exponentials, but in this case, I don't know if it really does too much with that. All right. So they're going to give you a graph, and they're going to ask you to find all kinds of things. All right. So, for example, let's do this. Oops. Let's look at, I didn't assign this, but we'll look at it anyway. Let's look at, if you have your book with you, on 61, it's problem number 9. Okay? And on problem number 9 on page 61, here, maybe I can, if you don't, in case you don't have it. Does everybody have a book thing or not? No? Let's see if I can do this guy. Okay, I want to do this. Let me pause this for a second. Let's talk about symmetry here. To the x-axis, to the y-axis, and to the origin. The origin one's the hardest. So if I draw a nice parabola, that has symmetry over this y-axis because obviously if I take it and I fold it, they're going to match. Okay, so that's symmetry. All right, so it matches. Okay, so we would say, hey, that has y-axis symmetry. Y-axis symmetry. Okay? X-axis symmetry. Maybe the graph looks something like so the graph looks like this and looks like this. Not a function, but it has, okay, x-axis symmetry for the same reason. Hey.
Hi. Make sure I'm the right page. Sheila Corbin, I'm the one that's.
Oh, yeah.
I'm auditing.
Yeah.
Okay.
Yeah. No problem. Okay. So this would have x-axis symmetry. The origin one is the toughest one. So it's kind of like if you take it and you kind of bring it over here, it's going to rotate like 180. If you rotate it 180 degrees, it's going to kind of match up. All right. So this one here is going to match up with that one. It's really hard to see a origin symmetry. All right. The other ones are pretty simple, but you just have to kind of play with a few of them to get it. It's pretty hard to see it at first, but after a while you kind of picked up on it. I'm sorry, what was that? Yeah. Yeah, that's kind of how you gotta look at it. Okay. And that's pretty much all there is with 1.2. It was way less than we had for 1.1. Okay. So I think what I'm going to do is I want to give you some time to work on these, and then we're going to do a little Desmos activity and jump into 1.3, and then we'll be done. Okay. So let's resume this. Now we're probably going to do quite a bit of Desmos stuff, so I'm going to try to get some information on here, but I'm probably going to do a lot of Desmos stuff. All right. So what we're going to look at is the graphs of functions. And they're going to talk about these things: even, odd, okay, maximum / minimum points, and whether they're called absolute or local. And then they talk about intervals of increasing and decreasing. So that's what we're going to look at. So let's talk about even and odd functions first, all right? Because that I can do without having a Desmos around. Now, they bring up even and odd function stuff, but it's not, how can I mean, I guess I've seen it a few times, but it's not something they get really excited about, okay? But here's the definition of an even function, okay? So if we take, and we have a function f, all right, and we take the opposite of x, or the negative of x, and it's still the same function that you started with, then we say it's even. So for example, let's say that we have f of x equals x squared, all right, simple, basic parabola. If I take and put a negative x like that, which means I'm going to do this, okay? So, I'm testing to see if it's even. This says, I want to take the opposite of whatever x is, and I want to put it into this function, and I want to see what I get, all right? So, if I take and square a negative, obviously, what are we going to get there? If we square a negative, we're going to get positive, right? So, this is just simply x squared, which is what we started with. Okay? So, even, that's what we say. It's even. Okay? This is even. Now, one other thing, and we've done x squared a couple times today, and in the last section I said, hey, this function is symmetric about the y-axis. Well, guess what? It says in here that if it's symmetric about the y-axis, then it's even, okay? So if you graph it and you say, oh, it's symmetric about the y-axis, then it's automatically going to be even, all right? That's it. So you can, again, you can test it both ways. You can either put this little negative x thing in here, see what happens, see if you get the same result as you started with, or you can just simply graph it. Right? But that's the definition of an even function. All right. If I go with f of x equals x cubed, and I say, all right, I'm going to check and see what this does. Notice that I'm putting the whole negative inside with the cube, all right? Then I get this thing. So the question is then, is this the same as that? Are these two things the same? Thanks. No. Because this is a negative and that's a positive, so no. They're not the same. All right? So that's not even. All right? They got to be the same. So when you put this in here, this negative in there, you should get the same thing you started with. All right? And this is not. So this one's not even. All right? Should have been a resounding nope. Not even. Okay, so for odd, here's what it says to do. Kind of the same idea. You're going to take f of negative x, and if you get a negative f of x, then we say that it's odd. So how does that work? Well, let's try this again. Okay, same two functions. I'm not going to change anything. I'm going to put that in there. Well, wait a second. So here's this. Here's this. They're the same thing. But in order for it to be odd, I have to have a negative someplace. Okay? I got to have a negative somewhere. And I don't. I don't. So this one is not odd. Okay? It does not. It's not an odd function. So, nope, not odd. Let's go back to the cubic one. Okay, now all of a sudden, oh, I do have a negative. There it is, right there. Okay. So then this one is odd. Okay? Yes. It's odd. Graphically, if you can do that little origin symmetric thing, then you've got yourself an odd function. So this is symmetric about the origin. But that's like the harder symmetric one to do, graphically, okay? So you kind of might want to lean a little bit more this way. They give a good example here. Which one is that one? Oh, this one. Another cube, but they put a 1 there, okay? And they say, okay, well, is it even or odd? Well, we know if we do this, let's do this and check it out. So I'm going to put a negative there, cubed minus 1. So I'm going to get a negative x cubed minus 1. So, first thing I'm going to ask you, are these two things the same? Yeah. So x cubed minus 1 is the same as negative x cubed minus 1? No, they're not the same. All right? So, not even. It's definitely not even because they got to be the same. They're going to be even. Now, is it odd though? We got to be careful with this. What do you think? Think it's odd? I got one head shaking, no. I got one going like this. Okay. That's about 2 out of 10. My percentage is not too good. All right. Here's what this says. Remember, it says if this is equal to the negative of f of x, which means that it would have to be equal to the negative of x cubed minus 1. Okay? So it's not just the leading term, it's the whole function. So if you distribute this minus inside here, yeah, that looks good, but uh-oh, that does not. Okay, so this is no. It's not odd, and it's not even. It's a neither. So when you're doing them, you have to kind of be careful. I think testing for even's pretty easy. You could basically just graph it, look at it, see if it's symmetric. But for the odd one, when it says it has to be the opposite, it's the opposite of the whole function. You want to make sure you kind of check that out. Okay? So that's odd and even functions. Right? You'll have a few questions on those. I think I asked one or two of them on the quiz and on the test, but not a whole lot. All right? I'm not too... Sound like that's a crucial part for me. Okay? Let's do max and mins. And I'm just going to sketch a graph and then we'll do some Desmos stuff. Okay, so max and mins. So a maximum and minimum occur when a graph reaches its highest point or its lowest point. All right, so whether it tops out or bottoms out. So right here, this would be a maximum, and this would be a minimum. But if you listen to what I said, literally you'd say, well, wait a second, this thing's going to keep going, so isn't there going to be lower values in here? Yes, you are correct. That makes it a local minimum. And a local maximum. The local just tells you that, the local is just saying that if I restricted this graph from here to here, then this would be the highest point, right? And this would be the lowest point. So in other words, I can take and restrict a graph to any interval that I want, right? So I can even go here and say, well, this would be a maximum, right? If I even go from here to here, well then now that becomes the maximum point, right?
So
any chunk.
When you're writing that, we would then say that the local min or max is at between these two points, or what have you, or...
No, yeah, well, I'm going to show you exactly how to handle that, okay? So a local maximum minimum are going to be your maximum minimum points within a certain region or a certain interval, okay? That's what those are. If we have a graph that looks like this, okay, then this is what we would call an absolute maximum. Because there's nothing higher than that point. Okay? So that's an absolute maximum. And vice versa, if I made the U shape like this, then this would be an absolute minimum. So there's absolutes and there's locals. So the locals are kind of, you know, where, yeah, there could be more numbers higher than that, lower than that, but those are just called the local ones because you could restrict it to a certain and get that, okay? That's kind of how you think of it, all right? If there's no points lower or no points higher, then those are absolutes, okay? So, for example, let's just do this, and we'll graph some. Oops. I'm going to just go. Okay, so I'm just going to type some stuff in. You guys can follow along if you want to. Y equals, I'm going to put them in like, I'll just put them in like this. It's easier for me to do it. Oops. Okay. Here's what I'm going to look for, right? So here's a cubic, goes on forever in both directions. Right? Here is my local maximum. I'm going to click on it. Okay? Or you're just going to tap on it, wherever you want. If you're not sure how to use Desmos, you just tap on it if you're using your phone. Okay? Click on it if you're using the computer. There it is. Make sure that when you tell me this is a local maximum at this point, 189 negative 24.19, something like that, just around it. Okay? I want the whole point though. And a lot of times, people just give me either this or this. But it's a point. It's not a number, it is a point. Okay, so the maximum point localized is here. All right. To go find the minimum one, just move it around, zoom out, whatever you want to do. Click. There it is. Okay, it's very easy to find them. 3.5, negative 1.37. Right? You just type them in, tap on where they are. Desmos tells you. It's awesome. Right? I'll get it once. There we go. All right, so here we have another one, okay? Move out of the way. Right down here. What's that one? I mean, what kind of maximum point is it? Minimum. Nothing's lower than this, okay? This graph's going up, it's going up. So we would say negative 3.2, negative 16.9, get around at 17 points. But that's an absolute. What's this one? Local. Okay. Local minimum. All right. What's this one? Local max, right? Okay. So, I mean, I think you probably have a pretty good feeling for what those are, because it makes sense. All right. Some mathematics actually makes sense. Okay. And that does. All right. And again, all you got to do is click on them. Click, click, tells you what they are. Okay, so darn easy. So that's local maximum minimums. What happens is that in the text, what they do, and this is what caused a little bit of issues, is they give you these parts of graphs, and they ask you what they are. So let me go back to this, kind of give you an example. So they like to do this. They have a graph, and they have one. I'm looking at one here where they go like this, start here, it goes down, it goes up, and it ends right here. So they call this 5, they call this 2, and they call this 1, 1 right there, and this one 4, 4. Okay? So the question is, are these absolutes, okay, or locals? All right? So, kind of tricky, but what is that one? Is it absolute or local? Why is it absolute? Does this graph ever go higher than this 4 here? What's that? It stops here and it stops here. It's got to be an absolute. Okay? What's this one though? That would be a local because this one drops a little lower. See? This is at 0, that's at 1. So it's tricky. Alright? They try to trick you. Okay? So make sure you're understanding the difference between when these guys end and when they don't. Okay? So maximum, local, that's where that would be a minimum for that one. Okay? So that's what they do. They have some ones like that. You got to be careful with that. Okay? And they pretty much show you when they have arrows and when they have endings and stoppings and so forth. Right? Last thing. Intervals of increasing and decreasing. Well, this is the second to last thing, but the other last thing is pretty quick. So anytime that a function is increasing, as we go left to right. So as I move left to right on this graph, it's sort of like a roller coaster thing. So it's going up. So we would say that it's increasing. At a certain point here, which we call that maximum point, it's going to top out, and then it's going to go down, and it's going to bottom out, and it's going to go up. So what we want to do is go increasing, decreasing, increasing, and write those intervals out. So we would find these points, whatever the heck they are. So let's say this one's 1 and 8, and this one's -3 and -5. And I would write those intervals of increasing, decreasing. How would I do that? For increasing, exactly, -infinity to 1. Okay? Now, I'm using interval notation with some parentheses rather than brackets because at 1, it's neither increasing or decreasing. So if you think about it, it's going to hit right there at the top, and it's really not doing anything. It's just at that very instant, it's just sitting there, okay? So increasing there, decreasing. Notice I'm only looking at the x's. Don't care about the y's. Care less about them on this. So from 1 to -3, again, parentheses, all right? I'm decreasing. And then finally, I'm increasing again from -3 to +infinity, all right? That's how you do it, okay? That's intervals of increasing, decreasing. So if I jump back to here, all right, and show me there we go, maybe, all right, I'm going to go back to this one. Okay, intervals of so from -infinity, give me that point, -1.89. So I'm going to write down on my paper from -infinity to -0.189 or 188, whatever, I just round it. Okay. It's increasing. All right, from here to down here, whatever point that was, it's decreasing. Okay, it's kind of nicer on a phone because I think you can get better screen actually by using your swiping. So from -0.189 to 3.5, decreasing. From 3.5 to +infinity, it's increasing. All right. So rise, fall, rise. But you always use the x's. Always use the x's. Turn this one off, turn this one on. Okay. Here, decreasing from -infinity to -3.25. So we go decreasing, we abbreviate it, -infinity to, I don't know, I put commas there, -3.2, something like that. Okay, increasing, -3.2 to go up here, snag this point, click, there it is. Okay, and now here I'm going again. So now decrease to 1. And then finally 1 to infinity. Okay.
So if you ask us for the rate of change, would you just put a union before between them, and then that's enough?
Well, that was the next thing I was going to mention was the rate of change thing. Okay, so on the rate of change, what they want you to do, and I don't think I asked a whole lot on that, but on the rate of change in here, this is like a calculus idea for those you are moving on to that.
Yeah,
So it's the change in y, oh, sorry, my bad. Change in y over the change in x. All right, and they'll give you a function. And they'll tell you to figure it out find the rate of change from 1 to 3. So then you would just go, okay, I'm going to go f of 1 first, figure out what that is. Good, right? Now I'm going to figure out what f of 3 is. So my rate of change is going to be the change in y over the change in x, which would be 26, because that difference is 26 over this difference, which is 2, which is 13, okay? So that's what the rate of change is in that. And they mention it in here. That's all they do with it. So, and it's, I mean, I'm not against them mentioning it, but it's a calculus idea, and it's kind of a cool idea, but they don't do much more with it than that. Okay, I think if they were to mention it, they probably should do a little bit more with it. Right? That's all you're doing, though. Okay. Yeah. So, like, this would have been more interesting, that problem, if we said, well, what's the rate of change between here to here? Okay, and that's just this basically slope of that line. And what is it from here to here, and so forth. And basically what you do is you get it down to what is the slope of that line at a point. That's what calculus does. It's a definition of a limit. So that makes it kind of interesting, but they don't do that for it. They just pick 2 points and do it, okay? So if we were to find the slope at that particular maximum point, it'd be 0, because it's like this. So if you think about that roller coaster, right? At that one point in time, it's not doing anything. It's just kind of, this instant, it's just sitting there. Okay? I don't like roller coasters myself, but that's what it does. Okay. So that's the rate of change stuff. I think that's pretty much all there is in here. Okay. And if you find something, you can always email me. All right. I do try to check that email at least every other day. So I do try checking it for you. So don't be afraid to do it. And you can ask me any questions you want when we come back on next Saturday on anything, and we can talk about it, whether it takes 5 minutes or an hour. It doesn't matter to me. And I don't think I have much more. Does anybody has any questions on anything? Yeah.
So I didn't find it like how the increasing and decreasing intervals. So
Yeah, absolutely. We can go back. So on this W then, so you're going to go left to right on this graph. Okay. So as we go left to right, starting at negative infinity, going here. This graph is falling down to here. Okay, so that's a decreasing interval. So I would go from negative infinity to, that was negative 3.2, that point down there. So that is decreasing. Well, once you get to the bottom of this point now, you're going back up. So that would be increasing. You get to that point, which was 0.77 to 1, I think it was. Maybe 0.77, I think it is. And then once you get to that, then you're going to fall again. See? It's decreasing. Yeah, so it's up, down, decreasing, increasing, decreasing, decreasing. Okay, down, up, down, up.
So it starts with like a downward arrow, and that's, what would that be? What would be increasing?
It starts with a downward arrow.
Like an example, it would be, maybe you just go left to right, right, on the side, and go down and follow that.
Oops. So this one is, so you go left to right.
That's the same as the last example, but like, what about this example that you gave earlier? So like, this one, it's, the arrow is downward, so like, would that be increasing?
They go left to right, it's going up.
Okay.
Yeah, they're just showing you that function's just flying down that way. Okay. Yeah. Good, good. Thumbs up, you're happy? Okay. If you have anything, I'll be happy to hang out here, you know. But that's all I really have for you today. So if you want to stick around, you can. If you don't, have a great day. Don't tell people I'm letting you out early though.
Thank you, you have a great day.
Yeah, thank you. You betcha. Sure, sure. Yeah, I can do that. You just want me to make something up then?
No, I just some of the notes I want to write down. So can you go back to
Oh, you want me to see what I wrote? Okay, got it. Got it.